So I'm going to say a few words talking about how the discovery that topology plays a major role in quantum materials has really affected our worldview. I'll say a bit about the general overview, and I'll tell you a little bit about the particular case of samarium hexaboride, which particularly fascinates me at this time. My collaborators in the work that I'll mention today, my recent collaborators are postdoc Poyao Chan, who is at Rutgers, Ona Erten, who is currently a postdoc at Dresden, and my old-time friend Alexei Svelek of Brookhaven National Labs, plus the cast of characters you can see below, including experimentalists. We've written a review of topological condo-insulating behavior in samarium hexaboride, which I wanted to draw to your attention here, and I'll talk a bit about a preprint that's just about to come out. So that's my outline in the next 20 minutes, and I'm going to particularly spend a lot of time on the rise of topology, how the discovery that topology plays a role in momentum space has affected our worldview. And then towards the middle of the talk, I'll switch to talking a bit about samarium hexaboride. And what I wanted particularly to do at the beginning was to try to discuss how three threads in our field, that of emergence, that of strong correlation, and that of topology, are intertwining in the way we are doing things, and how this provides a tremendous opportunity for research at the current time. So if you look at the timeline of condensed matter physics, one of the key elements in our frontier field has been emergence, the discovery that as you put things together, new things happen. You get snowflakes, you get magnetism, superconductivity, even life. And this, in some sense, is the nature of the frontier that we're exploring. And perhaps one of the early contributions to this emergent worldview was Landau himself, in particular with the Landau theory in the 1930s. But I want to also emphasize the other threads. Of course, correlation, the role of interactions, has also been part of the theme of condensed matter physics over the last 100 years, and it was realized very early on that phenomena such as the crystal, ferromagnetism, are driven by interactions, strong interactions amongst electrons. The topological thread has been a more recent comer to the field, and probably the first realizations of the importance of topology really came in real space with vortex lattices, liquid crystals, and the Kosterlitz-Thouless transition, which this year has been noted, will be noted this weekend with the Nobel Prize to Kosterlitz-Thouless. And in some sense, the last time that these three areas came together was BCS theory. BCS theory brought together emergence, brought together correlations, and unexpectedly gave us, through the flux lattice, the notion of topology. Its emergent impact is well known. It led to the Anderson-Higgs effect, and that discovery impacted our colleagues in particle physics. It's led further along the way to the discovery of strongly correlated materials, high temperature superconductors, iron-based superconductors, and their low energy cousins, the heavy fermion materials. But the evolution of topology has really come in a rather unexpected direction. One of the first areas in which topology in momentum space was first understood was through the integer quantum Hall effect. This then led to the fractional quantum Hall effect, and the realization that these are topological states of matter led to the proposal of Z2 topological insulators and the profusion of new discoveries, the possible connection due to Kitaev of Majorana fermions to qubits. And what we have now is an opportunity to realize a collision between these three threads again. It's an opportunity for a new storm of discovery. In fact, one of the things I wanted to mention is that this is a discovery which in some sense is a time-action replay of a discovery that could have been made about 70 years ago. And the discoverer of the transistor, Shockley himself, was one of the major players in understanding surface states. And this is a phys rev a picture of a phys rev that Shockley wrote in 1939, which you can look at online, in which he looked at a type binding model of P states and S states. It's a very simple type binding model. At that stage, 8 sites was about the maximum they could calculate. But already they saw, and Shockley noticed, that as an odd parity and even parity state cross, in periodic boundary conditions, parity is conserved and they don't cross, but when you break the periodic boundary conditions with open boundary conditions, the odd and even states repel one another and form edge states. And Shockley was so struck by this that he thought it might be a general principle and suggested that diamond would have surface states. In fact, it turns out this suggestion was wrong. He didn't know about the role of topology or the role of spin-orbit coupling in its connection with topology. And that discovery had to wait another 70 years. And so we've got a lot of catching up to do right now. Let me just mention with one view graph about the rise of topology. This is really the remarkable, connected with Wigner's remarkable observation that sometimes mathematics appears in physics quite unexpectedly. And mathematically, topology describes manifolds in geometry. And what has been discovered is that the differential geometry of the wave function can give rise to new forms of topological order. And in the early days, this really came out of a study of the integer quantum Hall effect. And one of the key theoretical ideas is the notion of a Berry connection. And although we attribute this to Michael Berry, in fact, one of the ideas of its connection with topology occurred a few years earlier in Thouless's 1982 paper, in which he introduced what we now call the Berry connection. And Thouless realized that the topological configurations of this vector potential in momentum space were what drove the integer quantum Hall effect. And I think that's one of the reasons he's being recognized this year, in addition to his contributions to the Kosterlitz-Thouless transition. And of course, the realization that this intertwined with spin-orbit coupling could lead to topology in the absence of time reversal breaking is part of this tremendous new revolution taking place. And so this then is the rise of topology. And in a nutshell, one of the ideas is that you can entangle the wave function, that a band crossing of odd and even parity states can give rise to a Z2 topological insulator. And this is just a totally cartoon. The fact is that once you put this twist into the wave function, you form surface states on the edge of the topological insulator because there's no continuous way to go from the vacuum to the artificial vacuum inside the topological insulator. And we know how to characterize this topological insulating state. The number of crossings, if it's an odd number, describes this kind of Mobius strip twist in the wave function, and we can use that to identify whether a band structure is a strong topological insulator or not. This is a field which is still developing very rapidly, even without interactions. And I just want to bring to your attention some recent developments that have taken place connecting the symmetries of crystals to the topology of a wave function. Particle physicists know that when you have the vacuum, you have the Poincaré symmetry. And this leads to 3 basic types of fermion. The Dirac fermion, which is the massive fermion, the electron, the Weyl fermion, which is massless, and the Majorana fermion, which is neutral. And in particle physics, by the way, the Weyl fermion is what we call the Dirac fermion, just to confuse matters. But the amazing thing about matter, when it's condensed, is that you break the Poincaré symmetry and you break it down into 230 space groups, each one its own separate universe. And over the last few years, theorists have been discovering the wide variety of different kinds of fermions that become possible in those 230 space group environments. And recently, Bradley et al. Have actually been able to classify all 230 space groups and all possible gapless fermions that are possible. To give you an idea of the kind of thing they've done, here's a result of theirs where they looked at space group number 199 and space group number 214. And in this case, there's something more than a conventional Dirac fermion. They actually find a threefold degeneracy at a crossing point, and they can connect that intimately with the point group and space group symmetries and the topology. And just as the biofermion gives rise to exotic surface states, this threefold degenerate state gives rise to a profusion of interesting Fermi arcs. In fact, this is an ongoing development, and there's another paper coming out by the same group at Princeton in the next few months, which actually purports to characterize all non-interacting topological insulators. Okay? So you might think that the game is up, but of course, that's only half the story, because real topological matter has interactions. And so whilst the topological quantum matter community can already set foot and start looking for new kinds of devices, we're also thinking about what happens when interactions interplay with topological matter. And it leads to all sorts of new ideas. The notion that we can have perhaps new forms of interacting matter with new kinds of excitation. If we can have Majorana fermions as point excitations, can we have them as bulk excitations? It also leads us to revisit the idea of topology in real space and to re-examine the possibility that our list of broken symmetry states is perhaps not complete, that the idea of Landau's idea of broken symmetry can be enriched. And lastly, it leads us to think that there may be new rules and new principles to guide us, still to be discovered. So I could really stop here, but what I'm going to do is illustrate some of these thoughts with samarium hexaboride. Samarium hexaboride is a topic of long-standing interest. This is a cubic material closely related to lanthanum hexaboride, which is actually a cathode. It was used extensively to make cathode ray tubes as the cathode in cathode ray tubes. But if you replace lanthanum by samarium, which introduces a local F moment, you transform the properties from a metal at high temperatures into an insulator with a narrow gap at low temperatures. It has an insulating gap that opens up at 50 Kelvin. It's kind of mixed valent. And it develops an unusual resistivity plateau below about 3 Kelvin. And this resistivity plateau was always there, and people tried to understand it in terms of conventional insulating behavior. Was it some kind of mid-gap state produced by impurities? There were immense studies trying to adjust the impurity quality in this gap. This plateau always stayed. And so in the new environment of topology, it raises the natural question, could this be shorting due to the formation of topological surface states? And once we learned the simple trick from Fu and Kane of how to calculate whether you have a twisted topological ground state, we realized that we could use this to analyze samarium hexaboride. And after we made our proposal, Takamoto came and worked out the detailed band structure of the problem. And the basic idea is that if there's a D in F in band inversion of this system, it occurs at 3 points, at the X point. Since it occurs 3 times, you should get a strong topological insulator with 3 Dirac cones on the surface. Experimentally, this led to studies to try and see if there's a surface conductivity, and this is one of the early studies by Kim et al. Showing that the Hall constant derives from the surface. As you change the thickness of the wedge, the Hall constant doesn't, the Hall resistance doesn't change, showing that this is a surface contribution. You can also look at the surface conductivity by doing non-local transport experiments, the work of Wolgast et al. And finally, you can look at this system using ARPAs, and you can confirm that the D-band crosses at the X point. And therefore, if this were a non-interacting system, it would be game, set, and match. This would be definitely a topological insulator at low temperatures. You can look at ARPAs, and you can also try and look at momentum resolution, and there's definite signs of surface states. This is really pushing the ARPAs to the limits of its resolution to see these surface states. While I was sitting here last night, Mohammed Hamidian said, but we've now seen them using STM. And I just want to quickly flash a view graph that he sent me this morning, showing perhaps the observation of light and heavy and heavier topological surface states on this strongly correlated topological condo insulator. So, since this is a meeting where we're supposed to be thinking not about frontiers, not just about frontiers of intellectual physics, but also how to detect them and how to devise mid-scale devices that might detect them, I thought I'd give you for a few moments a theoretician's perspective on this. Please forgive me for my ignorance. One of the things that is fascinating to all of us is the fact that we can look at DC properties under a wide range of conditions. We can measure specific heat, which I like to think of as a crude way of measuring entropy and hence entanglement entropy. We can measure resistivity as a function of temperature, field, and pressure. Susceptibility is a function of temperature and field. And these DC probes give us a wide spectrum of ways of following the properties of matter under tunable conditions. Here is one picture of ytterbium rhodium 2 silicon 2 showing how by tuning with a magnetic field you can see a quantum critical point at a finite field where the non-Fermi liquid goes all the way down to very low temperatures. Here's another picture taken from recent work by Stern et al. In which they take samarium hexaboride and they strain it. And one of the curious things is that when you strain it at low temperatures and then you warm it up with no strain, you see signs that the plateau can actually survive in the presence of strain up to higher temperatures. And this is a matter of great interest. It's as if the characteristic energy scale in samarium hexaboride is increased through the application of shear strain. So here is another example of how you can, by using extreme conditions, you can get new insight. But of course, what we really like to do is to look at spectroscopy. And spectroscopy gives us this additional axis of energy that probes the excitations. And we can do electron, photon, neutron spectroscopy, various kinds of spectroscopy. And these give us frequency-dependent information, which is completely invaluable. However, in this case, we're much more limited as regards how much tuning we can actually accomplish. And so one of the things that's highly desirable is to have spectroscopy under tunable field and pressure conditions. And I know this is starting in the community, but we need much more information along those lines. We'd love to know, to look at the spectroscopy of samarium hexaboride under strain conditions, for example. Okay. But samarium hexaboride is a nice example because the experimentalists have given us the insight that it may be topological, but along the way there are some enduring mysteries which show that this is probably not the end of the story. There may even be two phases lurking in this material. There's a marked indication that when you have flux-grown samples and when you have image furnace-grown samples, they have slightly different properties. And it's those slightly different properties that seem to be there in the image furnace-grown samples that I want to emphasize. Okay? Of course, it does seem to have topological surface states, and it does, therefore, have the unique position of being one of the first strongly interacting topological insulators. But it's got strange bulk properties. The specific heat, measured for a very long time, has a large linear component. There is the linear specific heat capacity that you can measure, and this is the work by Fallon et al. Typically, somewhere between 10 to 50 millijoules per mole Kelvin squared linear specific heat is seen in these samples. Where is this coming from? Lanthanum hexaboride, which is a metal with a large Fermi surface, has a much smaller linear specific heat. That's rather remarkable, given this is an insulator. Okay. And the quantum oscillations seem to not indicate that you've got surface states. They're not sensitive to the surface states. They seem to be picking up something in the bulk. And one of the indications of this is that although the surface conductivity dominates the conductivity, you don't see Shubnikov-de Hassel oscillations. No one's ever seen them in this material. But you do see oscillations, and they seem to be best analyzed by analyzing them as bulk oscillations with a bulk Fermi surface. So there's some disagreement on this between the different groups. I can't show you the most up-to-date data because it's not yet published and you're filming it, but I assure you that data shows that this Fermi surface is extraordinarily three-dimensional. The thermal conductivity is also weird, and here I can show you unpublished data which is taken from a camera shot I took at the March meeting from Suchitra Sebastian's work, showing the thermal conductivity, which is proportional to the field at low temperatures. This is truly remarkable. Here's the field dependence at 100 millikelvin. What kind of state of matter gives you a linear in B thermal conductivity? It reminds you of a flux lattice. Okay. And the optical conductivity, again unpublished work, shows that in the floating zone systems, grown systems, that you have, although it's a DC insulator, it seems to be an AC conductor with a lot of subgap states here. What's causing this? Is this connected with the linear in field thermal conductivity? Is this connected with the linear in temperature specific heat? Is this connected with the crazy de Haaspen-Alphen oscillations? This is the mystery of the material, and it's got theorists scratching their heads. So I want to end with telling you about one of our ideas on this. We're thinking, and we may be delusional, that it might be a failed superconductor. Now you may laugh at that. How could this possibly, this nice insulator, be a failed superconductor? Okay. Well, and this is where topology comes back into the story, because superconductors are actually topological ground states themselves. A superconductor is not just a superfluid, it's a charged superfluid. And it has local gauge invariance. And our colleagues, the particle physicists, have long been telling us that we shouldn't think in terms of an order parameter, because there isn't one. Because if you imagine applying a pairing field to a superconductor and now slowly removing that pairing field, unlike a ferromagnet where you stay in the polarized state, in a superconductor, Elitzer showed a long time ago that as you remove the pairing field, it averages over the full orbit of the superconductor, and you have no order parameter left. The only thing that's left in a superconductor is its topology, which is the fact that superfluidity and superconductivity depends on the ability to form topologically stable quantized circulation. And it's this quantized circulation that allows a persistent current to run around a ring when you turn on a magnetic field. And this is rather interesting, because if you remove that topology, you wouldn't have a superfluid. You presumably wouldn't have a superconductor, so what would you have? And in the case of superfluids, we have one example of this, which is superfluid helium-3A, where the order parameter lives on a higher manifold, and it doesn't ever form a perfect superfluid. It has dissipation in its ground state. So we've been playing with a model of samarium hexaboride, which involves a composite order parameter, a bound state between spins and pairs. And this composite order parameter is rather unique because it's triplet, but it has no orbital angular momentum. And so unlike conventional triplet order parameters or higher angular momentum pair states, it doesn't log to the lattice because it doesn't have the orbital component. Its spin component is analogous to a spin-half ferromagnet, and as a result it can be isotropic inside a cubic environment. And this then means that its manifold is the manifold of the group SO3, which doesn't allow Z vortices, doesn't allow the quantization of circulation. And so even if this doesn't apply to samarium hexaboride, it's an interesting notion to explore. So in the case of samarium hexaboride, our model involves the use of Majorana fermions to describe the spin. It's a model which we actually played with back in 1993 until someone pointed out that we discovered a superconductor, not an insulator. And so we wrote a series of papers on the concept of odd frequency pairing, and only one paper contained the allusion to samarium hexaboride and its linear specific heat. But the basic idea is that when you hybridize d electrons, which are consistent with 4 Majorana states, spin up, spin down is 2 Majoranas for up and 2 Majoranas for down, with a spin, and a spin could be thought of as a vector of Majorana fermions. As you know, Pauli matrices anti-commute, they're real, they're just like a Majorana fermion. So you can represent the spin as a cross product of 2 Pauli matrices or the cross product of 2 Majorana fermions. When you hybridize them, one gets left behind, and so you get a gapless Majorana band of d electrons. And these guys are rather interesting, and in fact a very simple, dumb calculation of the spectrum in the presence of a vector potential gives you this quantized spectrum you see here in red. And basically the idea is that this gapless Majorana band Although the linear in vector potential coupling vanishes, and therefore they're neutral, the quadratic in vector potential part survives, if only you can make it gauge invariant. So we've tried to look at this order parameter. We've written down a long wavelength action for it. And one of the interesting things is that this order parameter allows for the presence of skyrmions, even though it doesn't allow for the presence of vortices. And skyrmions cost energy to create them. But in a magnetic field, you reach a critical field where actually they start to condense. Once they condense, they don't like to form a vortex lattice because they have no long-range interactions. And they don't like to get pinned because they have no core. And so rather like the vortex state of the cuprates, they'll form a non-superconducting state. We think that non-superconducting state allows the penetration of electric fields and is therefore a dielectric. And we can, sorry, I missed one thing there. And so we can actually estimate the critical magnetic field where the Meissner effect will develop. And this critical magnetic field is determined only by the Kondo temperature, the V Kondo, the lattice spacing, and the speed of light. And when you work it out, it's about 1 Gauss. So the prediction of this crazy theory is if you take samarium hexaboride and you put it in a mu metal shield, which screens out the Earth's magnetic field and can safely take you well below, 1,000 times below a Gauss, you should see a Meissner effect. Okay? That's a crazy theory. And let me just mention a few other things. One of the other systems that may be topological in the heavy firmament systems is cerium nickel tin. This system is a non-symmorphic insulator. It's a semi-metal, and one of the results of this extensive analysis of topological states of matter is that non-symmorphic crystals have glide symmetries that can protect surface states. And they lead to these rather exotic surface states with a winding, which the Japanese community calls a Mobius insulator. In North America, they're called hourglass insulators. And so here's cerium nickel tin, which is a semi-metal. If you put antimony in it, notice it develops this plateau. And there's lots of arguments over what this plateau is due to, but the simplest explanation is it's probably got surface states. And there are other examples of this, these kinds of behavior. There's cerium 343, and these may be wide examples of states which can be examined for interesting behavior. And I think I'm finished there. Thank you.